So we are working on the kinetic molecular theory lab. It says, do not write on this paper, write the answers on the answer document, and the answer document is on the 3rd page. So here's where we're going to write our answers. So let's go through it. The first thing says start on the intro screen. So we're going to open up the lab. And the intro screen's here. It says blue particles are blank while red particles are blank. So if you open up particles here, let's make this smaller. It says right here, blue particles are heavy, red particles are light. So we're going to write it right in there. Okay. Then it says, before moving forward, make a few predictions. So you don't have to be correct here. Make predictions. So we've made predictions. Now we're going to answer 3A, which asks, put 1 pump of heavy blue gas into the container at room temperature. Describe how the particles behave over a span of about 30 seconds. Do the particles ever stop moving? Well, I've already put 1 pump in here, and we're watching it. How are the particles behaving? Let's observe them. We've observed that the particles don't stop moving. Some are moving faster than others. They change speed according to collisions. And now we're going to fill in this chart. It says put 1 pump of heavy blue gas. We have done that. And then we did A. And now it says count the wall collisions by hitting the green play button. Let's do that. We come over here. We click on this collision counter. And then we click the green play button. It's going to simulate 10 picoseconds, which is a trillionth of a second. It's going to simulate 10 trillionths of a second. Here we go. And count the collisions in that trillionth of a second. So you can see the simulation's obviously slowed down a lot. And it tells us there's 34 collisions in 10 picoseconds. We're going to write that down here. 34. Now, it's interesting to note that we run it again, you're going to get a different number. Now it's 36. Just pick one. On average, it should be the same. If you do enough of them, you'll find an average. Okay. So we wrote that down. Now it says it wants a pressure reading. We come over here, we read the pressure. It says 5.8 atmospheres of pressure. We learned that last class. That is our most common unit for pressure, is an atmosphere of pressure. At room temperature, standard temperature and pressure at sea level is 1 atmosphere of pressure. And then it says describe the particle of movement. We really have nothing to compare it to, so we'll just say the particles are moving. We'll compare that later. We have nothing to compare it to. We've only had 1 so far. It says we want to add heat now by dragging the marker up 10 seconds. So we're going to bring this up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Last part says, describe the motion of the particles at this point in time. How do they compare to room temperature, which is the previous one? Faster, slower, messier, neater? Be descriptive. We're going to write faster and messier. I love it. Okay, good. Now it says decrease the temperature. Cool the gas down by dragging the marker down to 80 Kelvin. This K stands for Kelvin. We can switch between Celsius and Kelvin. They are equal when we switch. Now we're going to go to Kelvin, and we're going to cool it down to 80 Kelvin. We're going to hold the ice here till it gets to 80 Kelvin. And you can slow this down. You don't have to hold it all the way down. As you get close, you can just slow it down to a crawl. Just pull it down a little bit. We're going to get to 80 Kelvin. Oh, I missed it, so I can heat it up a little bit. There it is. And it says count the wall collisions, record the pressure, and the motion of the particles again. So it's told us to go to absolute zero for the last part. Absolute zero is 0 Kelvin. I've cooled this down till this says 0. Absolute zero is the coldest possible theoretical temperature. It cannot be reached. They've never reached it in a lab. They've only come within fractions of a 1 Kelvin. So even though I keep trying to cool this, you'll notice that these particles will still move almost imperceptibly, but they are moving. You cannot stop particles from moving. Why? Because theoretically, if particles go to 0 Kelvin and they stop moving, they will have 0 volume. But matter cannot have 0 volume. By definition, matter has mass and takes up space. So it cannot have 0 volume. It has volume. So now we're going to describe what's happening at absolute zero. So we have marked down absolute zero, 0 wall collisions, 0 pressure, and no movement or activity, or at least imperceptible. If you do watch it, though, over time, you will see that these particles are going to get closer to that wall. And you can even see this. This one seems to be slowly separating from the wall, I think. You have to watch it a long time. Anyway, we're done. Office hours on Thursday, 1:45.